Université de Bourgogne, who's going to talk about random tensor networks with local Haar-averaging. Please.
Okay, thank you. So, well, let me thank everyone for being here and the organizers for this very nice conference, sorry. And so just like Luca, it will be in the same spirit as Luca's talk. So slightly off topic, but hopefully you will take something out of it. So and more precisely, I will try to review some well-known results on what's called random tensor networks and tell you a bit why people are interested in these models. So in short, to understand like generic features of many-body quantum systems regarding their entanglement structure. Okay, I will spend some time with slides, like explaining some background material, and then hopefully, if time allows, I will switch to the Blackboard to give you some kind of a new calculation. Yeah. Okay, so here's the outline. So I will review some background material that Luca may have mentioned already on the notion of entanglement and the notion of how to measure it. Then I will give you a kind of sketch of why people, especially in high energy physics and many-body physics, why people tend to try to understand entanglement in terms of geometry. And then I will review a specific model where this relation between entanglement and geometry is very clear and can be studied very neatly. And these are these so-called random tensor networks. And finally, I will discuss a kind of a richer version of this type of random tensor networks that we are exploring with Luca, where we get kind of a richer entanglement structures and that we are hoping to develop further. Okay. All right. So let me start by reviewing what entanglement is, and just starting from the bipartite situation. So entanglement always refers to a partitioning of your systems. So here I will start with the partitioning in two subsystems. So you have a tensor, the global Hilbert space is a tensor product of two Hilbert space, the left and the right. And a generic state in this Hilbert space can be encoded into some kind of matrix here. And what, colloquially speaking, what people call entanglement are like any features of these states that are not intrinsic to any one of the two subsystems, one or two, okay? And from this kind of colloquial definition, you can come up with various definitions depending on the operational context. But one kind of overarching notion of entanglement that Luca mentioned already is one based on the notion of local unitarity, invariance. So what you are asking, what you are calling entanglement data is really anything about the state psi which is invariant under local changes of basis in the subsystems. Okay, so this is basically invariance under U of D1 times U of D2, where D1 is the dimension of H1 and D2 is the dimension of H2. And so in the bipartite case, these invariants can be classified very easily thanks to the singular value decomposition. So you know that any rectangular matrix like this, you can write it in this form, a unitary acting on the left Hilbert space times a diagonal matrix times a unitary acting on the right Hilbert space. And the eigenvalues of this diagonal matrix are contain everything you need to know to recover these invariants under local unitaries. But to generalize to the multipartite case, it's useful to adopt a slightly different description. But let me first introduce like this kind of notions that people use in quantum information. Usually, they introduced reduced states associated to psi. So you can either trace this operator over the second subsystem and obtain a reduced state on the first subsystem, which in terms of this matrix here is simply M dagger, okay? Or you can do it on the other subsystem and you get M dagger M, okay? And so another way to specify the singular values of M is just by specifying the spectrum of M dagger or that of M dagger M, which is the same, okay? And from there, it's quite clear that you can also, if you wish to, instead of working with eigenvalues, you can work with a trace invariance of this form. So you take the matrix M dagger M to some power, you trace of it, and that gives you basically the some information about the eigenvalues. And if you know all of these traces, you know all of the eigenvalues. Okay, and so these are the type of invariants that generalize well to tensors. And as Luca explained already, it can be represented neatly in terms of pictures. And so here, in the case of these matrices, I can represent a matrix by a dot with two lines, one green, one red, corresponding to the two indices. Black dots would be the conjugate matrix. And then these trace invariants, they are cycle graphs with alternating colors here, okay? So in particular, in this bipartite case, it's clear that you get, in this representation, you get one invariant per order, one connected invariant per order n here, okay? So not so many invariants. All right, and then in quantum information, people don't usually work directly with these trace invariants, but they take some log of it and rescale by some factor, and this is what people call Rényi entropies, okay? I mentioned this because it will be a bit relevant later. You may also know about von Neumann entropy of the reduced state, which is defined by minus trace of rho log rho. So these quantities, they are specific functions of the whole entanglement spectrum of the system. But they are useful because they tend to, in quantum information processing, they tend to characterize when a certain task is possible or not. And typically, the von Neumann entropy is the one that is most relevant operationally, but it's harder to compute. So people tend to compute Rényi entropies as a proxy to understand von Neumann entropy. Okay. And here's a very simple example. So for Bell state that Luca also mentioned, which has this structure, the reduced states are just proportional to the identity, and the spectrum is just flat. So you have one eigenvalue, one over d, appearing d times. And in terms of entropies, they are all equal. So the Rényi-2 entropy, for example, is equal to the von Neumann entropy that you can think of as the Rényi-1 entropy in some sense, and which is also equal to the log of the rank of the matrix, which you can think of as a S0. And this is, I mentioned this here because in random tensor networks later, we will see that we get nice properties, where the entanglement spectrum is flat in the sense that S2 equals S1 equals S0 at leading order. And this is what we would like to depart from with Luca in some sense. All right. Okay, so now let's move on to multipartite entanglement. It will be a bit quicker, I guess. So here, what's happening is that we are trying to define entanglement now with respect to a subdivision into Q subsystems, 1, 2, up to Q. And the state, as a result, is encoded into tensors with Q indices. And so now we don't have a good notion of eigenvalues of this tensor or singular value decomposition, but we can still try to define the entanglement spectrum of the state as just the collection of all the trace invariants that we can define in the same way as in the case of as in the bipartite case. So they parameterize all there is to know about local unitary invariants in general. So and here's an illustration for Q equals 3. So now the tensor is still represented by a node, but I have 3 half edges coming out of it now. And the invariants are going to be exactly as before, can be represented by colored diagrams, which are bipartite. So you have white vertices and black vertices, and every node, there's exactly one edge of a given color that is incident to it. And now the key observation here is that the number of invariants, so the number of the numbers you need to fix to completely fix the entanglement structure of the state grows like factorially with the number of times. Okay. So there is a lot of information in fact, most of the information about the state is in the entanglement structure, not in the local structure. Okay, and this begs the question of, okay, but what do we do here now if we want to, yes? What's so everything I say is at large D, but yes. Where was I? All right. And so this begs the question a bit like in practice, which invariants are more important than others, in particular in this large D limit where we can hope to say something. Okay, and just because I will use these notations later, instead of colored diagrams, colored pictures, we can encode these invariants into tuples of permutations. So for example, here I have two copies of the state in some sense. So two white dots, two black dots. And I can encode this diagram into three permutations, one for each color. And here is just the 3 times the identity because I send the white vertex number 1 to black vertex number 1, etc. in all the colors, and same for 2. And here in this example, you see that I'm swapping now the 1 and 2 with respect to the green color. And so I have one of the entries, which is not the identity. And this kind of representation is redundant, of course, but you can see that a diagram like this with 2 n nodes and q colors is equivalent to a list of q permutations up to this transformation. So you are allowed to multiply by a diagonal permutation on the left and on the right. And this was, yeah, in fact, I cited it before here, but this was studied here in this paper. Essentially. And this is a way you can enumerate, in fact, these invariants. Okay, so in the rest of the talk, I will use interchangeably like these two notations, trace of B of T bar T or trace of tau of T bar T, with tau defining B. Okay, and the kind of general question we are interested in is, as I said before, so which of those many invariants are most relevant to characterize multipartite entanglement structures in many-body quantum systems? Okay, and we will study this in simple time models, of course. All right, now I would like to do something a bit risky, which is to say, talk about things I don't understand very well, but kind of a good motivation for this work. So I will try that. So the point is that in many different fields of physics, it seems that there is a really deep relationship between bipartite entanglement and geometry, in particular, the geometry of interfaces. And this comes up first in the context of many-body physics, where people found that ground states of gapped local Hamiltonians tend to be highly atypical in the sense that their von Neumann entropy associated to a given region here scales typically like the area of the interface between the region and the complement, not like the volume. And it's well known from a result by Page that, in fact, if you look at a typical state in the Hilbert space, this relation will scale like the volume of the region, not the area. So in this sense, the states that we care about, the ones that describe ground states of Hamiltonian systems, they reside in a tiny corner of the full Hilbert space, and that's essentially the motivation for the invention of tensor networks that I will talk about later. They are some kind of variational ansatz with a polynomial number of parameters in the system size, which obey these type of area laws by construction. And so that's why it's is such a big topic in many body physics because they are used in practice to study quantum systems, which would be unmanageable due to the system size otherwise. Okay. All right. And then a bit closer to the theme of this conference, there is also this kind of relationship between entropy and geometry in relativistic QFT. And this, for example, in the context of the Unruh effect, or equivalently, it's called the Bisoniano-Wishman theorem in algebraic QFT. So that tells you that in a Poincaré invariant QFT, verifying some axioms, like the details don't really matter. If you look at, if you take the pure state, the vacuum, sorry, of this QFT, and you trace over a half plane, half space, so this region here represented in blue, that generates a causal domain that is represented in red here. So if you trace over this, you get a state for this half space in blue here, which has causal domain represented in green. And what Unruh found, and Bisoniano-Wishman as well, is that the state here is a thermal state. So here I've written it a bit schematically. It's not literally this, but what I want to say is that it's a thermal state with respect to Hamiltonian that generates uniformly accelerated motions here in this wedge. And this is what is responsible for the Unruh effect, which is that a uniformly accelerated observer in vacuum would see will have his her measurement apparatus click even if it's in the vacuum, okay, with a rate that is specified by a geometric temperature here. Okay, and what I want to say is that this phenomenon is really tied to the fact that in these QFTs there is a universal divergence in the von Neumann entropy of the region here, which scales like the area, like it's a divergent quantity, but it scales like the area. And this has been taken up by people like Jacobson to propose like heuristic derivations of GR, starting from QFT plus some assumption about quantum gravity. So it's very heuristic, but I find it a bit fascinating. I wanted to talk about it. So, and the assumption is the following, is that this relation between entropy and area that you see in QFT, but which comes up with a constant which is really infinity in practice, is regulated somehow by quantum gravity effects. So Jacobson postulates that this relation holds, but in a rigorous way, due to quantum gravity effects that we are not able to describe. So there is a relation between entropy and area, and the coefficient is assumed to be universal and finite. So that's an assumption. If you make this assumption plus some kind of entanglement equilibrium hypothesis that I won't discuss, but some assumption that the entanglement equilibrates in some sense, and this is described by this entropy, you can show that this is equivalent to Einstein's equations. Okay, so so it seems that even at the level of quantum gravity, there seems to be a deep relation between entanglement and of the underlying quantum fabric of gravity and geometry. Okay, and this is what people are excited about, I guess, in quantum gravity these days. And there is so I don't want to spend too much time with this, but there is a holographic version of this that is more relevant for what I'm going to say later. And I promise you then it will be a kind of a concrete, and it won't be impressionistic like this. But so in ADS CFT, what people study, again, it's not my expertise, but they study situations where you are in a ADS D+1. So here I've represented a Cauchy slice of this ADS space. And on the boundary, you have a CFT in dimension D, and it is somehow dual to a theory of gravity, a classical theory of gravity in the bulk geometry. And in this context, people observe, like in specific models, a relation between. So if you take a region on the CFT, so on the boundary A, and you compute its entanglement entropy, you find that it again obeys some kind of area law, but of a holographic nature. So you have to look for regions here, gamma A, that are homotopic to this boundary A, and try to maximize this functional area of gamma A over 4G, where G is the Newton's constant. And you find that for the extremal surface here, that is here, computing the area of this extremal surface computes exactly the von Neumann entropy of the region on the boundary. And again, these people have used this relation in the other direction. They say, okay, let's assume that there is a relation like this, and then they can derive Einstein's equations from the structure of the CFT up to second order. But okay. What? Yeah. So here I had in mind dimension 4, but so gamma A would be a surface, but it could be any dimension. All right. So now enough heuristic pictures, but it's just a way to motivate what's coming next. But the conclusion, the take-home message from this is that bipartite entanglement and area laws seem to play a central role in various physical situations like many-body physics, relativistic QFT, and even quantum gravity. And the question is, does this interplay between geometry and entanglement extends to the multipartite setting, which is much less understood? And here I want to investigate this on simple time models, which are these random tensor networks. Okay, and now I'm going to be a bit more concrete. So there are questions on this? Okay. Okay, so random tensor networks, what are they? So they are just quantum states that you can associate to a graph G with vertices set V and edges E. And you will partition the set of vertices into a V bulk, which are these black vertices here that are supposed to be the bulk vertices, as in the picture I had before, and the boundary vertices that are represented in white here. But the structure of the graph can be anything. Here I've represented a kind of a disk geometry so that it's easier to visualize, but it can be anything. And then you associate an Hilbert space to each half edge of the graph, so which I label by E, an edge, and X, a given vertex of the edge. And this we will assume that all of these Hilbert space have a fixed dimension D, which is called the bound dimension of the network. Okay. And then you try to construct a global state, and the way you construct it is by specifying two pieces of data. First, a data that is associated to the set of edges. So you construct a quantum state, which is supported on edges. So you take the tensor product of all edges, and then you put a maximally, put a Bell state on each of these edges. Okay, and then you do a similar thing for the set of vertices. So you define a state as a tensor product over the bulk vertices, and here it's important that it's only bulk vertices, and some state associated to the bulk vertices, where the Hilbert space associated to a vertex is just the tensor product of all the Hilbert space of the half edges that are incident to it. Okay, is it clear? And then what people call a tensor network state in this context is just this quantity here. So you just take the inner product of the vertex states, which are support only on the bulk, and the edge states, which are support on everything. And what you get, so here it's represented here. So the green piece is this psi, and the red piece is this phi, and you glue them together along these circles here. And as a result, you get something that is entirely supported on the boundary, on the set of boundary vertices. So the Hilbert space is associated to boundary vertices. Okay, so that's a tensor network in this context. And a random tensor network is one where you sample for this state psi here. You know, it was a product over all the bulk states of some psi of x. You just take the set of psi of x to be independent, randomly Haar distributed vectors in the Hilbert space. So you probe them. You sample them with a Haar measure. So what that means in practice is that you have this moment relation. So the expectation value of the state associated to a vertex to tensored n times is going to be defined just by this quantity. So yeah, I take a global Haar average over this Hilbert space of some arbitrary state, which is immaterial because it does not depend on this choice of state. And I just compute these moments. And this integral, you can compute it by some, for example, representation theory. You can see that this operator, in fact, is the projector on the symmetric subspace of this tensor product here. And so as a result, it can be written. So what I want you to take from this formula is just that these moments, they can be written as a sum over some permutations that act on this tensor product here. So that swap the different tensor factors. So there is a sum of a sigma in Sn. So where n is the thing that refers to the fact that you are looking at the n moment. and then this operator, which I don't define, but it's just the usual, the obvious representation of Sn that swaps the tensor factors here, hx tensored n times. Okay, but okay, the details don't matter. All I want you to see is that there is an explicit formula for the moment, and that it involves permutations. Okay. Oh, it's not a function. It's just the representation of Sn that acts on the Hilbert space. So it's just the transposition of acting on this Hilbert space. Will swap the two tensor factors labeled by this transposition. Okay. So it's the obvious representation yeah. So okay. And now in this context, how can we represent the type of multipartite entanglement observables I had in mind before is as follows. So you can suppose you partition the set of boundary vertices into several regions. So here I have A1, A2 up to AM. And then from that, you can construct the tensor invariant that is associated to a given set of permutations that act on these n copies. So you have n copies of this state, you have a partition of the boundary, and then you have these permutations that act on the copies. And so this invariant is just the type of invariance I was describing before, but in this context of random tensor networks. And well, you can try to evaluate their expectation value. And okay, here it doesn't matter what this means. What I want to say is that people have done this computation, and the remarkable thing is that you find that the expectation value of this entanglement measure, multipartite, is to evaluate it at leading order. You just need to evaluate a kind of generalized spin system on the network, and the way it works is that you have a permutation associated to each vertex x in the bulk here, so it's sigma x. You have permutations that are fixed on the boundary. So so these conditions here, the choice of observables that you want to compute amounts to a choice of boundary condition for this spin model. And then you get exponential of minus log d, so the bound dimension, times some energy functional. And so you see that the log d plays the role of temperature. So when you send d to infinity, it's like looking at zero temperature. And the functional here can be expressed in terms of the Cayley distance on the permutation group. So it's like the number of transpositions you need to go from from sigma x to sigma y. And so it's a generalized Potts model in a way where the state lives on the permutation group. Okay. Okay, and so evaluating this entanglement observable at leading order amounts to determining the energy of the ground states of these systems. So there's a nice interplay between classical statistical physics here and quantum entanglement. And so just to be concrete, let's look at a simple example. So let's suppose I partition my boundary in two parts, A and A bar. And I want to compute the purity of this trace of rho A squared. So the simplest entanglement observable possible. If I compute this, I get an Ising model on the nose, because now sigma lives in S2, which I can identify with plus minus, you know, yeah, okay. And so trying to find the leading order contribution to this quantity here amounts to finding the energy of the ground state. And as you know, in this case, when you have a partitioning in two halves like this, what you need to look for are minimal cuts in the graph. So here I have a cut that cuts two edges. And once you have one such minimal cuts, you can just put all spins on the left to plus, like to the same as the boundary on the left. All spins on the right to minus, and this is going to be a minimizing. This is going to be a ground state. And so, as a result, what you see is that you have an area low here, which is of a kind of holographic nature, just like in a kind of a cryptic picture I had shown you before. So you have a boundary, and then you have an area low with respect to a structure in the bulk. Yeah, and that's it. And the additional point I want to say is that this value you find here in this specific context is maximal, in fact, because you can see that the rank row A is bounded by this same quantity. So this means that here we get always a kind of Ryu-Takayama formula for this type of systems, but it's a very specific one where the entanglement spectrum is flat. Yeah. Okay. Okay, and how much time do we have actually, Joseph? Ah, okay, that's good. Okay, now I'm going to switch to what we want to do next, which is we want to take this random tensor network platform, but instead of doing some kind of global average at each of the vertices, we want to average separately over the tensor factors that are associated to the alpha edges. What's the rational? The rational is that we want to identify, we know in this global averaging that leads to area lows, we want to identify which local entanglement pattern structures are responsible for this long-range entanglement structure. And once we identify them, we hope to obtain a richer entanglement spectra by selecting just specific entanglement structures, local entanglement structures. And so in particular, we want to depart from this kind of flat spectrum that is usually found in this context. Okay, and with this, I think I'm going to switch to Blackboard, if you don't mind. Yeah. So now I'm going to show you a simple calculation where we kind of write down the classical spin system that emerges when you do this finer type of averaging. So the only difference is what happens at the given vertex. So I will focus on a vertex here. Suppose it has some number of legs, which I label here, up to Q of X. So Q is the valency of X, the coordination number of X. And so what we are going to do is that we're going to define first a seed state here. So a state associated to this vertex. Let's do it like this. That's a generic entanglement and generic state in this Hilbert space. But here we're going to fix this tensor once and for all. Okay, fixed tensor. And now we're going to take this state and average not over the whole Hilbert space, which would completely erase any information we might have encoded in T, but only on local factors separately. So we will keep all the information which is about the entanglement structure of this T here. So, okay. So in short, we average over UD to the Q instead of U of DQ, which would be what you would do in the case of the case I described before. Okay, and so what we need to do to see what happens to this classical model, spin system, spin model that encodes the properties of entanglement in the system, is to determine the moments of this type of averaging. So I need to tell you what is this, what happens when I average over this U dq, this state here. And so let's look at the moment n. So I take n copies of this state and I average over ud to the q. And so so I don't know, is it clear what that means, or do I need to write the definition, or no, it's clear. Okay, so what you find is so in here, what you need to use is a Weingarten calculus. Oh, well. So in the previous case, you didn't need to use Weingarten calculus to evaluate these moments, but here it comes up handy. And what you find is that instead of having a sum over one permutation, you have a sum over q permutations, one per. Yeah. So you have a sum over sigma 1 up to sigma q in Sn of something that I will call ft of sigma, which I will define later, and some operator. So I won't write down what this operator is, but it's the obvious operator that swaps the different tensor factors according to the list of permutations sigma. Okay, so it's a bit cumbersome to write what it is, but it's yeah. Okay, and then I need to tell you what is this ft of sigma, and that's where you get some complications. So ft of sigma, what you find is that it writes again as a sum over a tuple of permutations. So τ1, τq in Sn. So you see it's a bit complicated. And then they come our beloved tensor invariants. So you see that this f is sensitive to the entanglement structure of T. So it is parameterized in terms of the invariance. And then you get a product over Weingarten functions. So again, I won't write what they are, but so for those of you who know Weingarten calculus, you know what these are, but I will just, what will I use? I will, yeah, that's all. Okay, and what I want to say is that, okay, typically what you find when you use a specific seed state here for T, you find that this is going to behave like d to the nq times minus some quantity that we'll call omega of T of tau. And this is going to be a positive quantity. So the leading order is going to be d to the nq. And then depending on the state and the combinatorics of these invariants, this tuple of permutations, you will get a suppression factor. So not all terms are going to be equal in this sum. And then similarly for these Weingarten functions, you know that they behave like d to the minus n, so which will cancel this guy, times d to the minus d of sigma c to c. So again, the scaled distance here that appears, times some combinatorial factor here. So here it's called the Bian-Speicher. No, Bian. Möbius function, but yeah, okay. So it's a combinatorial quantity that does not have a definite sign, so it introduces some difficulties here, but not, that are tameable. 5 minutes. Yes. Yes, that's what I wanted to say. All right. Okay, and okay, and so. What we have done is to analyze what happens, how we can evaluate this function here at leading order for various states T here, For example, we looked at what happens for when you take the GAZ state that Luca mentioned before, and a couple of others. And in all those cases, what you end up with is a spin model. So it's some kind of enrichment of the previous story I told you about. Okay, we do like this. Where spins or permutations are associated now to half edges instead of vertices. Okay, so let me draw it. So here, if you have two vertices here next to each other, you have one permutation here for each half edge. Y sigma 1 y sigma 2 y sigma 3 y, etc. And so on edges you have the same kind of Ising coupling that we had before. So you have a coupling which is proportional to d sigma 1 sigma 2 x, and on vertices you have a weight which is given by this function here. So it's a kind of relaxed spin model where you are allowed to have different sigmas around a given vertex, but where typically when you insert some kind of an entangled state like JZ, this function will be picked around the diagonal. So it will be picked around sigma 1 equals sigma 2 equals sigma 3 equals sigma 4. And so you will recover effectively the type of generalized Potts model that I was mentioning before. So as a result, yeah, I will finish on this. As a result, what we find in the first examples we have looked at, but is that typically for highly entangled states T here, you recover the same behavior as in the previous model, except that the Rényi-2 entropy, for example, is not maximal. So it scales in the same way. So you can find that S2, the expectation value of S2 scales like it scales like a certain constant times log D, but this CA is going to be in general smaller than the size of the minimal cuts, and so you get this open the way to have a non-flat spectra, which are slightly richer than in the previous model, and we are in the process of studying them. Okay, and I will conclude on this, and I will just say that yeah, so now we are kind of playing around with this quantity here, and depending on the structure of T, you get some omega here that is sensitive to different combinatorial aspects of the bubbles here. So it could be so you can choose a T that will give you for omega the number of connected components of the graph. You can choose one that will give you the number of bicolored paths. You can choose one that will give you the genus of a specific bedding of the graph, like the jackets. So you can recover all the type of structures that we have been studying in the context of random geometry with these objects. But here they affect the local structure of entanglement, and now it's a kind of tunable quantity that we can play with in the random tensor networks. Okay, and we'll finish on this. Okay, thanks.